So, in the last lecture we were discussing diffusion into an infinite medium, the decay of a pulse. Into infinite medium. So, basically you have the z, sorry, this is the x axis, x, this is z. You inject a pulse into the of total mass m, mass per unit area in xy plane. Mass per unit area in the xy plane is equal to m. This is injected at t equal to 0, at t is equal to 0, and then this spreads on both sides. So, if I look at the concentration field, initially it will be sharply peaked close to the origin, and as time progresses the height will decrease, whereas the spatial extent will keep increasing. The spatial extent keeps increasing and the height decreases. The concentration I defined as m times delta of z, where delta is the delta function, delta of z is equal to 0 for z not equal to 0, and the integral dz delta of z is equal to 1. So, those are the two conditions on the delta function. So, we had to solve the concentration equation, partial c by partial t is equal to d partial square c by partial z square, with the boundary conditions c goes to 0 for z going to plus or minus infinity, c going to 0 for plus or minus, z going to plus or minus infinity, and this integral condition has to be satisfied for all time. Integral minus infinity to infinity dz times c has to be equal to m, for all times. So, how did we solve this? We had defined the similarity variable psi is equal to z by root dt. This is the similarity variable because there is no other length scale in the problem. From the z coordinate, time and diffusivity, I can create only one dimensionless group. And I had defined c star is equal to c by m by root dt. Because if root dt is the only length scale, then the only concentration scale is m by root dt, because m is mass per unit area, and if I divide by root dt I will get mass per unit volume. That is the only concentration scale. So, using these two similarity variables, I had got a similarity equation in terms of psi. In terms of psi, I had got the similarity equation minus d minus 1 by 2. Minus 1 by 2 d by d psi of psi c star is equal to d square c star by d psi square. So, that was the similarity equation which I got by transforming the equation in terms of the original concentration c and t and z into an equation in terms of c star and psi. I had solved this equation to get c star is equal to 1 by 2 root pi e power minus size, let me write it a little bit more clearly, c star is equal to 1 by 2 root pi e power minus psi square by 4. This was a Gaussian function. a Gaussian function which if I plot, okay, as a function of psi, if I plot C star, okay, it is a bell shaped curve, okay, which has a maximum at the origin, symmetric, and it goes to 0. Okay. Okay, this is the C star of psi. It goes to 0 as psi goes to plus or minus infinity as required by the boundary conditions, and this normalization factor 1 by 2 root pi that I have used here, okay, implies that this condition is satisfied. Okay. So, that implies that this condition is satisfied, that is integral minus infinity to infinity d psi into C star is equal to 1. This normalization condition is satisfied by this function. Okay. So, that is the equation for the concentration field, the scaled equation for the concentration field. I can rewrite it in terms of the dimensional equation. Okay. C is equal to m by and note that the maximum concentration is at z is equal to 0, because that is the point of symmetry, the point where we initially injected the concentration. Therefore, the maximum concentration is equal to m by 2 root pi dt, okay, at the location where we first injected the pulse. Okay. You can find out the extent of spreading of the pulse by taking the variance of the concentration field sigma z square, which will be equal to integral minus infinity to infinity dz of z square c by z c. Okay. This turns out to be equal to 2 times d times t, okay, which implies that the standard deviation sigma z is equal to root of 2 dt. So, the pulse spreads in such a way that the maximum concentration decreases 1 over root dt, and the extent, the spatial extent of this pulse increases proportional to root dt, okay, in such a way that the total concentration is a constant. Okay. So, that is the expression for the decay of a pulse. Okay. Okay. Now, this same calculation can be extended to 2 and 3 dimensions. Okay. I will just go over the 3-dimensional calculation. Okay. I will just go over the 3-dimensional calculation. The 2-dimensional calculation emerges just by analogy. Okay. We will not be able to solve it by similarity transforms. You can do it in a radial coordinate system, but I will not do that here. I will just tell you what the solutions are. Okay. In 3 dimensions. Okay. The equation is partial c by partial t is equal to d into partial square c by partial x square It turns out that the solution for this is the product. So, the boundary conditions are that c tends to 0 for x, y and z going to plus or minus infinity, okay. Okay, far from the origin, the point of injection. Okay. For x, y and z going to plus or minus infinity, c has to go to 0. Okay. And at initial time, okay, in 3 dimensions, okay, at initial time in 3 dimensions, I inject a finite amount of mass at the origin. Okay. At t equal to 0, there is a finite mass injected at the origin. Okay. Okay, a finite mass that is injected at the origin, okay, at x is equal to 0, y is equal to 0, z is equal to 0. At this location, I inject a finite amount of mass m, okay. And then I want to ask, how does this mass, this concentration spread as time progresses due to diffusion, okay. So, how does this concentration spread in 3 dimensions due to diffusion? Okay. Now, what is this mass injected at initial time? Okay. So, that means that I am injecting a finite amount of mass into an infinitesimal volume. Okay. I am injecting a finite amount of mass into an infinitesimal volume in 3 dimensions. Note that in 1 dimension it was a mass per unit area that was injected, okay, not a finite amount of mass. Okay. It was a finite amount of mass per unit area injected within an infinitesimal spatial distance, okay, whereas here I have a finite amount of mass injected in a within an infinitesimal volume. Okay. So, this thing is written as C is equal to m times delta of x, delta of y, delta of z, okay, at t is equal to 0. Okay. The product of 3 delta functions. Note that the delta function is defined such that delta of x is equal to 0 for delta of z. Z not equal to 0, integral minus infinity to infinity dz delta of z is equal to 1. Okay. So, from this equation you can easily see that dz has dimensions of length. Therefore, delta of z has to have dimensions of 1 over length. Okay. Delta of z has to have dimensions of 1 over length. Therefore, I have a delta of x, delta of y, delta of z, each has dimensions of 1 over length. So, therefore, the right side has dimensions of mass per length cubed or mass per unit volume. So, therefore, it has the correct dimensions as concentration. This can also be written as a 3-dimensional delta function, okay, which is defined as delta of z is equal to 0 for z not equal to 0, okay, or x not equal to 0 or y not equal to 0. Okay. It is non-zero only when x, y and z are all equal to 0. Okay. It is non-zero only when x, y and z are all equal to 0. So, I should kindly note the mistake here, this should be a 3-dimensional delta function. This is equal to 0 for if any one of x, y, z is not equal to 0, then it is equal to 0. It is non-zero only when all x, y and z are all equal to 0. Okay. And we have the integral condition, integral minus infinity to infinity dx delta of x, y, z. This has to be equal to 1. Okay. So, that is the integral condition. Okay. So, you inject finite amount of mass within an infinitesimal volume. Okay. Concentration is mass times the 3-dimensional delta function. That 3-dimensional delta function has dimensions of 1 over volume. Okay. So, you have to solve this differential equation, okay, in 3 dimensions subject to this initial condition and these boundary conditions. Okay. Turns out that the solution is just the product of the solutions for each of the single particles. Okay. M by 2 root pi dt e power minus x square by 4 dt should be careful here. M into this is the solution in 3 dimensions, the product of the solutions in 1 dimension multiplied by this total mass injected per unit volume. Okay. Or I can also write this as m by 8 into pi dt power 3 halves, okay, e power minus x square plus y square plus z square by 4 dt. Okay. That is a 3-dimensional Gaussian function. Okay. Alternatively, I can also write this as m by 8 into pi dt whole power 3 halves, okay, e power minus r square by 4 dt. X square plus y square plus z square is equal to r square, where r is the distance from the origin, okay, where r is the distance from the origin. Okay. Indicating that these concentration field spreads in a spherically symmetric way, okay, as we would expect for this particular configuration, because you are injecting a finite mass within an infinitesimal volume at the origin, and the concentration spreads outward isotropically, okay, with time. Okay. Now, you can so in this particular case, as you can see in 3 dimensions, the maximum concentration, okay, C max, is at r is equal to 0. Okay, this is equal to m by 8 into pi dt power 3 halves. Okay. The characteristic length scale is root dt, therefore, the characteristic volume is dt power 3 halves. Therefore, the maximum concentration decreases as 1 over dt to the 3 halves as time increases. Okay. So, the maximum concentration decreases as 1 over dt to the 3 halves power in 3 dimensions. One can calculate the variance of the distribution as a function of r, for example, the spread radially outwards. Okay. This will be, you have to do an integral over all 3 coordinates of r square times c divided by the denominator is just equal to m, okay, that is the initial mass that was injected. The denominator is just equal to m, that was the initial mass that was injected. And you can see that because each of these 3 functions is normalized. Integral of this function 1 by root 2 root pi dt e power minus x square by 4 dt integrated over x is equal to 1. Second function integrated over y is equal to 1, and the third function integrated over z is also equal to 1. 3 identical integrals. Each of these are normalized Gaussian. So, the denominator is just equal to m, the numerator has to be evaluated. Okay. In the numerator, this r square, okay, can be re-expressed as x square plus y square plus z square into c. Okay. You can express r square as x square plus y square plus z square. Okay. I showed you that the integral of z square times c divided by integral of c was equal to 2 dt. Since this is spreading spherically symmetrically, integrals of x square, y square and z square are all identical. Okay. Each of those gives you 2 dt. That means that the total is equal to 6 times d times t. Okay. And therefore, this is the variance of the distribution. The standard deviation, the spread sigma r is equal to root of 6 dt. So, that gives you the radial extent of spreading. Okay. This gives you the radial extent of spreading due to a point source. Okay. The radial extent of spreading increases proportional to square root of dt. Okay. The radial extent of spreading increases proportional to square root of dt, whereas the maximum concentration decreases as 1 over dt to the 3 halves. Okay. So, that is, these are functions of the Gaussian distribution. Okay, the Gaussian distribution in 3 dimensions, which is just a product of the Gaussian distributions in the x, y and z coordinates. Okay. A similar calculation can be done in 2 dimensions, where you have just the x and y coordinates. Okay. There also we can get a Gaussian distribution, and that the spreading will be 4 dt, okay, because you have 2 coordinates. So, this is the a summary of the spreading of a pulse in one dimension and in 3 dimensions, and one can do that in 2 dimensions as well. I will leave that as an exercise. Okay. So, this is a problem that is for example, if you had some kind of a factory with a smokestack that emits some poisonous fumes, and you want to know what is the distance beyond which it is the maximum distance beyond which it is possible for people to live, for example, because the pollutant concentration has to be less than a maximum value for people to be able to live at a particular distance r from the location where the pollutant is ejected. Okay. You can estimate the distance and the time at which the concentration passes through a maximum. Okay. So, the concentration at a particular location is equal to m by 8 root of pi dt, 8 into power 3 halves e power minus r square by 4 dt. Okay. And if you are sitting at a particular location, and if you follow the concentration with respect to time, for example, the concentration as a function of time at this particular location, initially it will be very small, because the length of diffusion is much smaller than the distance to this location. The diffusion length root dt is much smaller than the distance to this location. As the plume spreads, initially it will increase, as the distance of spreading increases. However, as the distance of spreading is increasing, the maximum concentration is also decreasing as 1 over dt to the 3 halves. So, as a function further of time, this maximum concentration will decrease until it once again spreads so much that there is a very low concentration which is uniform. How do we determine what is this maximum concentration? So, we can do that, the maximum concentration as a function of time, by taking the derivative with respect to time, which is d by dt of and now you have to differentiate by chain rule. You have to differentiate this by chain rule. So, there is a factor here that depends on time, and there is a factor here also that depends on time. So, you have to differentiate it by chain rule, and what you will get after differentiating is that this becomes m into r square minus 6 dt divided by 32 pi to the 3 halves d to the 5 halves times t power 7 by 2 e power minus r square by 4 dt. That is what you get by differentiating the numerator and denominator. Denominator has t power minus 3 halves, so you will get minus 3 by 2 t power minus 5 by 2, and in the numerator you have r square by 4 dt. So, when you differentiate it, you will get minus r square by 4 dt square. And so, this minus and minus, you will get a plus sign on the first term, second term will have a negative sign. So, therefore, the time at which this passes through a maximum is where dc by dt equal to 0. It passes through a maximum where dc by dt is equal to 0, or r square is equal to 6 dt. Therefore, the time at which you get a maximum concentration is equal to r square by 60. So, after the pollutant is injected at a location distant r from the point of injection, the concentration passes through a maximum when the time is equal to r square by 6d, when the time is r square by 6d. And you can also find the maximum concentration by substituting this one into this expression here. And the maximum concentration turns out to be C max is equal to m into 3 by 2 pi e r square, okay, power 3 by 2. Okay. Okay. You just have to substitute t is equal to r square by 6d in this expression here. Okay. T is equal to r square by 6d. So, you get e power minus 3 by 2 over here. Okay. That is e that is the factor e over here, power minus 3 by 2. You get an r square because dt is equal to r square, and this becomes the maximum concentration. Okay. Okay. So, you can predict, given that you have injection of a particular mass of pollutant at a discharge point, right, what is the concentration going to pass through a maximum at some observation point that is at a distance r from this point. Okay. Of course, this makes a simplification. We have assumed that this is similar to injection into an infinite medium. Okay. In this particular case, you have the earth over here, okay, you have a ground over here. Okay. Okay. So, therefore, it is not similar to injection into an infinite medium. So, this is a simplification. We neglect the boundaries that are present in order to calculate this. Okay. There are ways to calculate it when boundaries are present, that we will see later in the course. Okay. But this is the mechanism of injection when you are injecting into an infinite medium, when there are no boundaries present. You can predict if a certain certain mass is injected, how does it spread? Okay. What is the time at which the concentration will pass through a maximum if you are at a particular location, and what will that maximum concentration be? Therefore, you can adjust this distance r in such a way that it is safe, okay, for habitation. Okay. So, this is one of the examples of application to a real system. Okay. So, this is using a similarity solution for transport into an infinite medium. We consider two cases. One is transport from a flat surface when the temperature or concentration at the surface is instantaneously raised to a finite value. The other is into an infinite medium. Here we have assumed that the concentration is a delta function. Okay. We have assumed that a concentration is a delta function at time t is equal to 0. This is an approximation. Okay. The concentration is not necessarily, you will always inject concentration into some particular location of some characteristic length L, okay, and then it will spread. Okay. Initially, of course, it will depend upon how it has been injected. What is the shape of the injection? Okay, whether it is what is the size of the region of injection? Okay. However, when it spreads such that, okay, the radial distance, okay, which is root dt, okay, when this distance root dt becomes much larger than the size of injection, then you can consider the initial injection as a delta function because it is of infinitesimal distance. Okay. So, this applies in the late stages, okay, when the length of spread of this is much larger than the size of the initial injection. Okay. In that case, you can approximate the injection or the pulse as a delta function. Okay. When the time after injection is such that t is much greater than L square by d, okay, which is the same as this condition. Okay. So, when you can when the time becomes large, initially the shape of the initial shape of the concentration field or the initial nature of the concentration field and the initial extent of the concentration field will matter. However, at long time, when the distance of spread is much larger than the initial extent, you can approximate the initial injection as a delta function, and then this similarity solution applies. So, this is an approximation for long time when the time is much larger than the extent of the initial concentration pulse divided L square divided by d. Okay. So, next class I will consider another example where we use similarity transforms, that is for a time dependent length scale. Okay. Okay, so, I will continue this in the next lecture. I will see you then.